Okay, so this is the last part of today's video. And so to explore the geometry of space-time, you see that apparently there's a geometry involved. Let's step away from space-time for a second and look at different kinds of geometric transformations. Let's consider rotations. Because you see, this reminds us of Pythagorean theorem. Let's look at the type of coordinate transformations in which there is an invariant quantity with a plus sign involved. Okay, in any case, let's consider rotations. Okay, so this is an aside. Okay, what happens under rotations? So let's say this is my coordinate system, and I have some kind of a segment right here. Okay, segment. What can I say if I look at a different coordinate system? So here's a rotated coordinate system. Oh, let me do this. Let me choose a different color. Okay. So here's a rotated coordinate system, x prime and y prime. Okay, so x prime, y prime is a rotated coordinate system. Okay. So what can you say? Is there an invariance involved? Notice in the original coordinate system, so here's delta x, or just x because the first point is at 0, but fine, let me stick with the delta notation. So this is, and this is a, and this is a delta y. Or you can just say x and y. What's the x prime and y prime? What's the delta x prime and delta y prime in the rotated coordinate system? What's the x component of that segment and the y component of that segment in the rotated coordinate system? Pause the video, think about it. So here's your segment. So you find the x component of the segment by projecting on the x-axis and the y component of the segment projecting on the y-axis. So you could just say, so this is and this is y. That's how you find the x and y components of a segment. How do you find the x and y components of the same segment in the rotated coordinate system? What do? You project on the x prime axis, right? So this is your right here. This is your delta x prime, right? And right here, this is your delta y prime. Reflect. If that doesn't make sense, reflect on that for a second. Okay, so under rotation, while the x and y components change from one coordinate system to another coordinate system, in this case, I'm looking at rotations of coordinate systems. Is there a quantity that remains invariant? Delta x changes, and y changes, that depends on the coordinate system. But throughout all this craziness, there is a quantity that remains invariant. Okay, so for rotations of coordinate systems, it's also an example of a transformation. It's a different type of transformation. It's not a transformation where one coordinate system is moving relative to another, but it's a rotation. It's another type of transformation. So for rotations, the quantity delta x comma squared plus delta y comma squared is an invariant. physical length of the segment, or length squared. And that's what I started with, right? I started talking about that you can place an origin anywhere. In this case, I'm keeping the origin, but you can rotate your coordinate system anywhere. The length of your house doesn't change. The length of your house is an invariant. The length of the segment is an invariant. So this is a Euclidean distance. So while a Euclidean distance remains invariant under rotations, a space-time interval remains invariant under Lorentz transformations. Okay. In other words, the invariance of the space-time interval is a geometric statement. You see, this is a geometry going on here. So space-time has a geometry. We can talk about a geometry of space-time. Okay. In the case of rotations, in the Euclidean space, in the XY space, the regular length with height space. In the case of rotations, one and the same point in space have different coordinates in rotated frames, right? And the locus of all these coordinates forms a circle. So let me draw. There's a geometry of spacetime, but first back to rotations. So here's a coordinate system, and let's say there's a point right here. So here's my house, here's a tree. And I choose this coordinate system. So in the black, so this is coordinate system, coord system S. So in S, that point is sitting here. I'm going to choose a different coordinate system, S prime. So this is my X prime, Y prime. And this is coord system S prime. So you see in S prime, the Y coordinate in S prime is smaller and the X coordinate is bigger. You see the X coordinate here was like this and the Y coordinate here was like that. In the S prime, that same point, that same tree, it's the same physical tree. In the new coordinates and the rotated coordinates, it has more of X and less of a Y, more of an X prime and less of a Y prime. So if I was to draw each of these coordinates separately, so here's my coordinate system S. In coordinate system S, the point is here. In coordinate system S prime, that point, that same point is here. And if I look at other coordinate, a set of all possible coordinate systems, that same physical tree, that same point, the same tree will be located on a circle somewhere. So you can see, so here's a circle of radius r, right? So the distance from the house to the tree is r. And in different coordinates, that house will be located at different points, but they all lie on a circle of radius r. I hope you understand that. So I can sort of look at all of these coordinates together in a sense. So here's the circle of radius r. And depending on which coordinate system you look at, depending on how the coordinate systems are rotated next to each other, that house will be located somewhere on this circle of radius r. Where depends on the angle of the coordinate. Okay, I hope you understand what I'm trying to say. So this is the x-axis is now the generic x-axis of each coordinate system. It's either x or x prime or x double prime, and this is the generic y coordinate of each system: y, y prime, y double prime. So in coordinate s, that house was located here. Coordinate s prime, that house was located here. I can use that color right here. In coordinate, s double prime, that house would be located here, and so on. All I'm saying is that depending on how you turn your head, that house, or sorry, that tree will be at a different angle relative to you. That's all I'm saying. I'm not saying anything fancy. I'm sort of calling your attention to the obvious. But depending on how you turn your head, the trees either here or here or here or here, and then you realize, oh, in all these coordinate systems, there is an invariant, that's r, and a set of points in all these coordinate systems forms a circle. Okay, I hope you understand this. So now let's go back to space-time. So before we go back to space-time, you see that a set of all these points forms a circle because the invariant is x squared plus y squared, or delta x squared plus delta y squared. Set of all points that are equidistant from the origin is called a circle. Set of all points for which x squared plus y squared is a constant is called a circle. Okay. Now back to space-time. In the case of Lorentz transformations, what's invariant is not x squared plus y squared, but basically x squared minus y squared, or delta x quantity squared minus c delta t quantity squared. C is just there because we're working in inconvenient units, meters, seconds. These units make no sense for relativity. In light years and years, it would be just one, or light seconds and seconds. But anyway, C is just along for the ride. The point is you have a two-dimensional space or space-time with a minus sign in the invariance. So in the case of Lorentz transformations in space-time, one and the same point in space-time, one and the same event, boom, an explosion. Okay, it has different coordinates in different co-moving frames. Okay, delta x is different from delta x prime, delta t is different from delta t prime, or x is different from x prime, t is different from t prime. But for all of them, this squared minus the other squared is the same. Okay, and so what do you call a set of points for which that quantity is the same? What do you call that? in space-time. It has a name, you know it since 9th grade. It's called a hyperbola. Okay, you're used to x squared minus y squared is a constant. That's a hyperbola. Okay. A set of points for which this is the same is a hyperbola. This is a hyperbola for which this thing is negative. And this is a hyperbola for which this thing is positive. So here, square minus ct squared is less than 0. And here, x squared minus ct squared is bigger than 0. Okay? Convince yourself of that. So again, if we have an event that in some coordinates takes place here, so this is my x and this is my ct, it's don't mind that I switch from the delta notation to the non-delta notation, because if it's an interval, I'm going to switch again. If it's an interval, you can place the first event at the origin, just to lighten the notation. So this is an event. So in some coordinates, this event lies on a hyperbola. Right? So let me try to draw that hyperbola. Okay. But in some other coordinates, that event will lie on the same hyperbola somewhere else. And in some other coordinates, that same event will lie on that same hyperbola somewhere else. And in some other coordinates or reference frame, in some other reference frame, that event will lie here, and so on. Just like delta x squared plus delta y squared is a measure of distance between 2 points in Euclidean space, the quantity delta x squared minus c delta t squared is a measure of distance between events in space-time. The quantity delta x squared plus c delta t squared cannot be a measure of the distance because it's not invariant from one frame to another. It's the quantity with the minus sign is what's invariant. So we think of it as a distance in space-time. It's not a physical distance. But by analogy, we think of it as a measure of distance between events in space-time. So delta x squared minus c delta t squared is a measure of distance in quotation marks. It's not a physical distance. And this is really just by analogy with delta x squared plus delta y squared being the distance in physical space. So this is a distance in physical space, and this is a distance in space-time. So space-time has different geometric properties than Euclidean space. And for those of you who are curious, it's also called Minkowski space, but don't worry about it. You don't have to know that. So notice that this quantity, and I'm hoping that it's not delayed right now, this quantity can be either positive or negative. You can say, well, how can distance be negative? Don't worry about it. It's not a physical distance, but it's a measure of distance, okay? Because it's invariant. And so it can be either positive or negative. And so space-time intervals are classified into different classes depending on whether the space-time intervals between a pair of events is positive or negative. So that's the next thing I want to talk about. So classification of space-time intervals. Why do we need to classify? Well, since the value of the interval remains invariant, its sign, SIGN, must be invariant too. So therefore, space-time intervals come in three varieties. So if delta S quantity squared is less than 0, this is called time-like interval. Now, why time-like? Well, remember delta X, the delta S squared equals delta X squared minus C delta T squared. So one way to make it negative if delta X is 0, it corresponds to two events that are separated only by time. That's where the name comes from, I think. So the name comes from the fact that we get the sign when two events are at the same location and they're only separated only by time. Notice, because the sign of the interval must be preserved under Lorentz transformations from one frame to another, if an interval is time-like, there exists an inertial reference frame accessible by a Lorentz transformation in which events take place at the same point. Okay, so if you have, so here's a hyperbola. If you have an event that's sitting here, so this is X and here's CT, there exists a reference frame in which that same event is sitting here. So if event is time-like, you can always find a reference frame accessible by a Lorentz transformation for which that event takes place exactly on the CT axis. Okay, a time-like interval, as seen from all those different accessible reference frames, forms a hyperbola, okay, with the foci on the time axis. Again, you have one and the same event, you can view it from different frames, and you will form that hyperbola. Okay, and so note that for time-like intervals, not note, but for time-like intervals, since the value of delta S squared is the same, so the value of delta S squared for that particular, or for a pair of events, or for that particular event, is the same regardless of what reference frame we're observing that interval from. And it's also the same in that reference frame in which that event takes place at the same location. So then this is purely a temporal separation. Well, that's just proper time. Okay, delta S squared minus equals minus delta tau squared. Okay, so the minus the square of the proper time interval in the frame in which the events take place at the same location is the square of the proper time. Okay, so time-like interval means that events are basically sufficiently close in space-time interval given the time interval. You can hop on a train fast enough, train such that you pass each event while sitting in your seat. So they all occur at the same location. Let's say you're in Slough and there's a concert in LA 7 hours from now. You hop on a train. Okay, so you start at x prime equals 0, and your train, just like in the very beginning of today's discussion, arrives to the location of that event. Let's say the event is right at the train station, and you're still at x prime equals 0. So there exists a reference frame, in this case, train's reference frame, in which both events, you leaving slow and you arriving to the concert, take place at the same location. So in that reference frame, the separation between events is purely temporal, and that's what this is. Okay. Now, the next situation is when delta S squared is bigger than 0, and this is called space-like interval. And again, if we go back to the interval, if the two events are separated only by space, you get a positive value. Okay, so if you have a positive value, it's still sort of more by space than by time. Okay, and that's where the name comes from the fact that we can get the sign when the two events occur at the same time and separated only spatially. And if an interval is space-like, there exists an inertial frame in which events occur at the same time. Okay, so again, so here's the x, or I guess here's x, here's CT. I think what I should add to this drawings is the light cone, right? So this is the light cone. This is light cone. Okay, so for space-like intervals, this hyperbola have foci on the x-axis. Okay, if an interval is space-like, there exists an inertial frame in which an event occurs at the same time as the first event. Where if we're talking about the intervals, meaning that there are two events, event 1 and event 2. So I'm always placing event 1 at the origin. Okay, and so if an interval between event 1 and event 2 is space-like, you can always find the coordinate system in which that second event occurs at the same time as the first event. Okay, you can always find the Lorentz transformation that takes you into that coordinate system. A space-like interval, as seen from all these different accessible reference frames, forms a hyperbola with foci on the spatial axis. Okay, and so for space-like intervals, delta S squared equals delta X squared. Okay, the square of the proper distance in a frame in which the events take place simultaneously. Okay, so this is proper distance. So before it was proper time, now it's proper distance. And what's the physical meaning of this? Well, space-like interval means that events are too far apart in space given a time interval, or they happen too close in time given the space interval. So you cannot hop on a fast enough train such that you pass each event while sitting at the same point in that moving coordinate system. You would need to travel faster than light for that. But there is a frame in which both events happen at the same time. So that's the space-like interval. And finally, there is this thing, and this is called light-like interval. Well, you can see where that name comes from. That name comes from the fact that we get this for two events that are connected by a signal traveling at the speed of light. Okay. A few points. Point number one, it is not possible to exchange an interval that's purely temporal for an interval that's purely spatial. You know how we discussed that as we switch from different frames, you can switch between, what's an element of space in one frame, in another frame, it has an admixture of space and time in that other frame. But you cannot completely flip an interval that's purely spatial for an interval that's purely temporal. Why? Because such intervals have different sign. And remember, sign has to be preserved under Lorentz transformations. You cannot jump into different frames. So in one frame, the pair of events are separated only by time, but another frame is separated only by space. Also, intervals between causally linked events are either time-like or light-like. Okay. So two causally linked events must be separated, or, okay, so this is time-like, and this is light-like. Light-like. A signal or an interaction propagating at the speed of light is used to link the cause and effect for the light-like interval. Third, ordering. We discussed ordering yesterday. Ordering of all time-like events is preserved. A change of a reference frame moves the interval around a branch of a hyperbola, but it must stay on the same branch. Thus, delta t stays positive or delta t stays negative. Okay, event 2 happens after event 1, or event 2 happens before event 1. But it's not true for space-like events. Okay, here the set of events lie in a hyperbola with a focus that lies on the x-axis. So you can be either above the x-axis, positive delta t, or below the x-axis, negative delta t. So so ordering time like events, or events that are separated by a time-like interval. Is preserved. So here's a hyperbola that corresponds to time-like intervals. Event 1 is at the origin, and you see, depending on, you can access all these points with a Lorentz transformation, but you can see delta t is always bigger than 0, or you can be here and delta t is always less than 0. Right? So event 1 is at the origin, event 2 is here or here. I hope it's not delayed, or here or here. Or event 1 is at the origin, and event 2 is here or here or here. So ordering the sign of delta t is preserved. So this is time-like. But for space-like, this is space-like. Event 1 is at the origin, event 2 is here or here or here or here or here. So you can see that delta t is bigger than 0 or delta t is less than 0. So that's what I'm trying to say. Okay. So the ordering of time-like events is preserved, but it's not true for space-like events. Time dilation is obvious in these diagrams. Okay, so if you have a time-like event, okay, so here's, so there exists a frame in which delta x between the events is 0. So here's your delta t. And we can see that for events that are separated only by time, where delta x is 0, delta t is smallest. I can switch to another reference frame. And now the separation between event 1, which is at the origin, and event 2 is bigger. So you can see it's a bigger delta t. Okay. In any other frame, other than the one where events take place at the same location, the events will have larger delta t. So time dilation is kind of obvious here. Okay. And note that here it's clear that time dilation only applies for time-like intervals, but it was implicit when we talked about moving clocks running slow. If the event was space-like, it would be impossible for the clock to move between the two events. There isn't a frame or a train fast enough for it to visit the two events such that they take place at the same location. So time dilation compares delta t with a proper time. And finally, okay, so I guess I didn't write explicitly, but you can see time dilation from these diagrams. And finally, note we can always set 0, 0 of any frame at the first event, such that delta x is just x of the second event, and delta t is time of the second event. So everything that I said about invariance of intervals then applies to just x comma t of the second event. Okay. For example, the space and time of the second event depends on the reference frame, but it will lie on the appropriate hyperbola. And basically, that's what I did here. That's what I did implicitly here. Okay. So, okay, today was really probably an unusual experience for you. And we won't go too much in the way of testing. You have a homework problem that involves intervals, actually a couple of homework problems that involves intervals. The main takeaway point is that today we got to really the heart of relativity, is that there exists a quantity that's invariant. So while space and time get mixed from one reference frame to another, there exists a quantity that stays constant, okay? And so if you have a pair of events, the space-time interval for that quantity has the same value and the same sign, regardless of what coordinate system you're using, or regardless of what reference frame you're using, rather. And you can make certain conclusions about that interval just based on that. Well, we have just scratched the surface on the geometry, but my hope is that when 10 years down the line, you hear someone saying something about the geometry of space-time, or space-time being curved. You might not know what it means, but you might say, oh, I see what I can kind of see how space-time can have a curvature, because space-time has a geometry. And that's all I wanted to say as far as the geometry is concerned. That when you do hear such things, it doesn't sound like Greek to you, so that even if you don't understand what it means, you can sort of relate and say, well, I believe that it makes sense to talk about curvature of space-time. All right, well, so we're going to start on momentum and energy, and we're going to do that for 2 more lectures. Hopefully we will finish relativity this week, and then we'll start on quantum mechanics next week. Okay, thanks.